3.5 Derivatives of Trigonometric Functions. Your objective for this lesson is to find and apply derivatives of the function. Let's start off with the derivatives of sine and cosine. You see here that the derivative of sine x is simply cosine x, and the derivative of cosine x is negative sine x. These are important. You do need to remember them, so memorize these. Example 1, find the derivatives of y equals x squared times sine x. This is part A. So you see that we have some multiplication going on here. We have x squared times sine x, which means that we are going to use the product rule. So dy dx equals our first term, x squared, times the derivative of sine x plus sine x times the derivative of x squared. So we have x squared, the derivative of sine x we just established is cosine x, plus sine x times the derivative of x squared is 2x, which gives us a final answer of x squared cosine x plus 2x sine x. Part B, y equals cosine x divided by 1 minus sine x. And here we have division, so we're going to use the quotient rule. So remember quotient rule, you have quotient rule, you have d dx of u over v is low d high minus high d low over low squared. So low d high minus high d low over low squared. So we have then dy dx is low d high, so d dx of cosine x, minus high d low over low squared. Okay. You know the derivative of cosine x is negative sine x. And the derivative of this, well, the 1 is going to go away. And derivative of sine x is cosine x. So negative sine x, we're going to have a negative cosine x. All over 1 minus sine x squared. Okay. Now I'm going to multiply this sine x into these parentheses so that I get negative sine x plus sine squared x. And over here, when I multiply these, I get a plus cosine squared x. And you should recognize one of your trig identities on the top there. I'll highlight that for you in case you don't, but we have sine squared x plus cosine squared x, which is equal to 1. So really, this is a 1. I'm going to rewrite that as 1 minus sine x over 1 minus sine x squared. And you should see something else that cancels now. We have this cancels as one of those. So really we're just left with 1 over 1 minus sine x. And this is our simplified answer, the derivative of our original function that we had up here. Okay. Simple harmonic motion, for instance, would be the motion of a weight bobbing up and down on the end of a spring. So going back and forth, gradually decreasing how high and how low that's bouncing. So looking at example 2 on page 136 of your book, we're talking about the position of a weight. We're told that the position of the weight at time t is s equals 5 cosine t. And we need to find the velocity and acceleration at time t. Now you know that velocity is your first derivative and acceleration is your second derivative. So basically we just need to find the first and second derivative of this function. So let's find v is ds over dt of 5 cosine t. Okay, and using the product rule, well, now we don't have to do that. This is simply 5 times negative sine t is the derivative of cosine, which is negative 5 sine t. So this is velocity. And acceleration is dv dt. So dv dt of negative 5 sine t, which will be negative 5 times derivative of sine is cosine. So a of t is negative 5 cosine t. Done. A jerk, I mentioned this in class before, but a jerk is a sudden change in acceleration. It is also the derivative of acceleration, which makes it the third derivative. So acceleration is the second derivative of the position function. The jerk is the third derivative of the position function. So you see here j of t is dA dt, which is d cubed s dt cubed. Okay. Example 3. The jerk caused by the constant acceleration of gravity, which is g equals negative 32 feet per second squared, is 0. So this is our acceleration, negative 32 feet per second squared. And this is a constant. You know that if we have a constant, if I graphed this is my axis, down here is negative 32 feet per second. It's a straight, flat line. The slope of this line is 0. So my derivative of the acceleration of gravity, negative 32, is 0. And I have a note here saying that this is why we do not get motion sick while we are sitting still. So sudden changes in movement are what cause motion sickness. Part B, the jerk of the simple harmonic motion from example 2 is j equals dA dt, which is d dt, negative 5 cosine t. So negative 5 cosine t was the second derivative, our acceleration function. And if we go ahead and calculate this, we're going to have negative 5 times negative sine t, which is 5 sine t. Okay. Derivatives of other trig functions. We have tangent. So the derivative of tangent is secant squared x. Derivative of cotangent is negative cosecant squared x. Derivative of secant is secant x tan x. And the derivative of cosecant x is negative cosecant x cotan x. Example 4. Find equations for the lines that are tangent and normal to the graph of f of x equals tan x over x at x equals 2. Okay. The first thing I need to do is find the derivative of this function. So dy dx of tan x over x. Maybe I should just say, sorry, d dx here. Is equal to, so we have a quotient, so x d dx tan x minus tan x d dx of x over x squared. Okay, so this gives me x secant squared x minus tan x, the derivative of x is just 1, so I'm not going to write anything else there, over x squared. Okay, and now I can just go ahead and plug in my 2 here. And this is what we get. So 2 secant squared 2 minus tan of 2 over 4. Okay. So this is our slope. This is our m for tangent. We also need to find the y value. So we need to plug in f of 2. We have tan 2 over 2. Okay. So, okay, we can set up the equation of the normal line now. We have y minus tan 2 over 2 equals our m, this very long function up here. Then x minus, we added 2, so this. Okay, now I'm just going to get the y by itself by adding this to both sides. So y equals this hot mess here. Plus tan 2 over 2. Okay, and we can enter all of this into the calculator to get a less intimidating answer here. You could leave it like this, and this would be perfectly accurate. We're going to have to do a little bit of rounding, that's okay. So if I enter this large fraction, that I'm circling in red, into the calculator, we're going to get this decimal here, so 3.433. This is 3.433, not sure why I just changed to blue. So that times x minus, so 3.433 times 2 gives us 6.867. So 6.867 plus tan 2 over 2, so tan 2 divided by 2 gives us minus 1.093. Okay, and last step is just to combine those two decimals. So negative 6.867 minus 1.093. We get a negative 7.96. Okay, so this is our tangent line. Of course, we still need to find the equation of the normal line. So remember, the slope of the normal line is the opposite reciprocal of the slope of the tangent line. So we had slope was 3.433, and for the normal line, so this is normal, the slope will be -1 divided by this. Okay, so we have y minus, our y1 was tan 2 over 2, equals this times x minus 2. Okay, and I'm going to simplify this with the calculator just like before. So negative 1 divided by 3.433 is negative 0.291. So negative 0.291 x. We're going to have a plus, what's this, times 2? Oh, well, it's a negative 2, so 0.583. Okay, and I also want to add my tan 2 over 2, which I can get from above. That was a negative 1.093. So negative 1.093. Okay. So simplifying this, we get negative 0.291x minus 0.51. And this is our equation to the normal line. Okay. One last example, example 5, and this says to find y double prime if y equals secant x. So let's start off by finding y prime. Can't find y double prime if we don't know y prime. We know already the derivative of secant x is secant x tan x. So then y double prime, we have to use the product rule. So we're going to have secant x times tan, the derivative of tan x is secant squared x, plus the derivative of secant x, well, I guess we should say tan x first, and then derivative of secant x is secant x tan x. Okay. And this simplifies to secant cubed x plus secant x tan squared x. And this is our answer. And that concludes 3.5, derivatives of trig functions.